Thank you, Catherine. It's very hard to follow the wonderful performance you just had from Cameron, and I'm going to tell you something about the planets and the way we see them. Astronomy is the grandest environmental science. Everyone's looked up at the night sky, interpreted it in their own way. Indeed, I like to say it's the oldest science except for medicine, and at the risk of insulting any medics here, perhaps the first to do more good than harm. But since we're in Trinity, we should start off with Isaac Newton, perhaps the best student we ever had here. It's been downhill all the time since then, Catherine. But he was a most unpleasant man, solitary and reclusive when young, vain and vindictive in his later years as President of the Royal Society. But I show him here because he must have thought about space travel. This is a picture from the English version of his great book, Principia, and it shows cannonballs being fired from a mountaintop. And if they're fired fast enough, then their trajectory curves downwards, no more steeply than the Earth curves underneath it. It goes into orbit. This is still the neatest way to explain the concept of orbital flight. Newton calculated that to go into a circular orbit, you have to fire your cannonball at 18,000 miles an hour. Not, of course, possible then, and not until 1957 did an object go into orbit. This was the Soviet Sputnik, followed by various dogs, and then followed by Yuri Gagarin in 1961. And 8 years after that, we had this iconic picture taken by the astronauts with the sterile moonscape contrasting with the delicate biosphere. This picture is still iconic among environmentalists. And I treasure this picture, signed for me a few years ago by 7 of the Apollo astronauts. Neil Armstrong didn't sign, but I once gave a lecture in America where he was sitting in the front row, seemingly taking notes. He might have been doing the crossword, I don't know, but it was a great honor to have him there. Well, of course, this was all a long time ago. The last men returned from the moon more than 40 years ago. You've got to be middle-aged to remember it. But subsequent to that time, no one's been further than near-Earth orbit, many, of course, circling in the International Space Station. But, of course, unmanned spaceflight has burgeoned. We depend on it technologically. Harvey Rail talked about GPS. We depend for environment and for communication. But for astronomers, space has been crucial. Telescopes have been sent above the blurring of the Earth's atmosphere, and unmanned probes have been to the varied and distinctive worlds of our solar system. So let me give you a quick tour of what it would be like. Well, you'd have an uncomfortable launch here in the rocket, and if you were heading outwards, if you look back from about 10 million miles away, you'd see something like this. This is the Earth and the Moon, with the Sun coming from this side. And then you would get to the red planet, Mars. And, of course, as has been said this morning, many probes have been to Mars to orbit it, to land on it. 3 years ago, this NASA Curiosity probe, about the size of a small car, which landed in where the oval is in the top left of that picture, and it's been trundling across this crater, which is about 100 miles across, and will eventually climb a mountain in the center. And if you look here near the bottom, you can see the track marks made by this. And it's already been about 15 miles, taking geological samples along the way and sending back pictures of the view, and you can see geological strata there. Well, so much for Mars. Going out, the next planet, Jupiter, the giant of the solar system. There have been probes going there, and also close-ups of its moons. These are the 4 moons discovered by Galileo in 1610, and they're very different. This is Io, which is sulfurous and volcanic. This is Europa, which is covered in ice. And here's a picture of the ice close up. Fascinating small worlds. And NASA's Cassini probe has been to Saturn. Here's a picture of Saturn and its rings. This is a rather nice picture. This shows an eclipse of the Sun by Saturn. Cassini is beyond Saturn, lined up at a distance such that Saturn blocks out the light of the Sun, but the Sun is shining on the rings. And the Earth, you can't quite see it, but it's at the end of that arrow, a long way away from here. And Saturn has its moons too. One of them, Enceladus, a small one, is covered in ice, rather like Europa. And we now know that there's definitely some liquid water under this ice. The biggest moon of Saturn is Titan, and Cassini carried in its cargo bay a European probe called Huygens, which was supposed to land on Titan. Titan had an atmosphere, so it landed with a parachute. And here are some pictures. The left hand and middle were taken on the way down, the right hand where it landed. This was a marvelous feat of robotics because a light signal takes hours, so it was on its own, it wasn't being controlled from the ground. Well, this may look a rather nice place with rivers and a little lake, but the temperature's minus 160 degrees centigrade, and the liquid is methane, not water, so not a very salubrious place. Going a bit further, we already heard mention of the European Rosetta probe, which was launched with the aim 10 years later of catching up with a comet, and it sent back pictures of this comet, which is now at about its nearest to the Sun, and the issue is whether it'll break up into two. It's got this sort of hourglass shape. We'll soon know that. And this is a small lander that was actually landed on the comet. And again, we had this summer, in July, the NASA New Horizons flyby of Pluto, and here's one of the first pictures that was sent back. Incidentally, what's deeply frustrating to the people involved in these two last projects is that the technology is more than 10 years out of date, because they've been on their journey to Rosetta or to Pluto for 10 years, and of course you freeze the design before that. And if you think of how mobile phones have advanced in 10 years, you realize how much better they could do now if they could use the most modern technology. But it is rather amazing that we had these pictures back from Pluto, which is 10,000 times further away than the Moon, sending back these pictures. Well, I would guess that in the next 50 years, small robotic probes will monitor and study all the bodies of our solar system in detail. More than that, I think we'll have huge robotic fabricators in space. Solar collectors, huge gossamer-thin telescopes, and maybe things on the Moon. And they will mine the Moon or mine asteroids. But will people follow? This is Harrison Schmitt, the last man on the Moon, and are people going to go back? Well, we're going to hear about this from Lars in the next talk, but let me give my take on this, is that the practical case for sending people into space is getting weaker all the time with each advance in robotics. But nonetheless, I hope people will go into space. I hope people now living will walk on Mars, but I think they will go as adventurers, not for any practical goal. And that's why I think the private sector is so important, because the trouble with NASA and ESA is that they've got to achieve high safety standards if they're sending publicly funded astronauts. NASA's shuttle crashed twice in 140 launches. Test pilots were happy with 2% odds, but each of those was a national trauma. So I think we've got to not regard this as space tourism, but as space adventure. And the kind of people who go will be people like Sir Ranulph Fiennes and people like that who are prepared to take very high risks. And I hope some of them will go, and we know that SpaceX is offering people going into orbit. I gather there's a company that's offering a trip round the backside of the Moon and back. That takes 5 or 6 days. I'm told they've sold a ticket for the second flight, but not the first flight, which might say something. But by the end of a century, I hope there will be people on Mars. In fact, Elon Musk of SpaceX says that he hopes to die on Mars, but not on impact. And he's now 44, so 40 years from now, he might well make this. And I hope also by the end of a century that there will be self-sustained communities, either on Mars or freely floating in space. And they will surely want to use all the advances of cyborg technology and genetic modification to adapt to an alien environment. We might want to constrain that sort of thing here on Earth, but we wish them good luck, surely, in adjusting themselves so that they can live in a different environment from the Earth. And this will be the start of the post-human era, because they will, in a few centuries, be a different species. There'll be some mix of organic and inorganic, we don't know what, but that'll be the start of a new phase in evolution. Is there any life out there already? There could be something swimming under the oceans of Europa or Enceladus, but no one expects very much in our solar system. But if we widen our horizons to the realm of the stars, far beyond the range of any probe we can now construct, then things are very different. They're very different because we now know that most of these stars are orbited by a retinue of planets, just as the Sun is orbited by the familiar planets. This story started 20 years ago when two people at Geneva discovered the first planet around a star, and one of them, Didier Queloz, is now a professor here in Trinity College and is a world leader in what's, I think, the most exciting area of astronomy today, which has led to the discovery of thousands of candidate planets around other stars. Let me mention just one of the techniques they use. It's very simple in principle. If you're looking at a star and there's a planet in orbit around it, and we're observing in the plane of the orbit so that it transits across, then the star will be slightly fainter when the planet's moving across in front, because it blocks out a bit of the light. If you're looking from beyond the solar system at the Sun, then when the Earth moves across it, the Sun will get fainter by 1 part in 10,000. So a signature of planets is dips in the brightness of a star, which repeat regularly each time the planet comes around. And there have been various techniques to do this, in particular a spacecraft called Kepler, which for 3.5 years pointed at an area of sky about 7 degrees across and measured the brightness of 150,000 stars to a precision of 1 part in 100,000, and did this over and over again, look at each star once every hour. And it found literally thousands of cases of planets. And of course, by this technique, you can infer the length of the year on the planet from how often it comes round, and something about the size of the planet from how deep the dip is. And this is a sort of rather silly cartoon which shows to scale many of the planets that have been found by Kepler. But special interest attaches to planets like the Earth in two respects. First, about the mass of the Earth, about the radius of the Earth, but secondly, at a distance from their parent star, such that water can exist, neither staying frozen nor boiling away. Because these are the planets on which life would be most likely to evolve. And there are a couple of candidates already which fit these descriptions. Now, it's a bit frustrating that we only, as it were, see the shadow of these planets. We can't, with any of our telescopes now, actually detect the image of planets. To explain why it's so hard, let's imagine that we had some aliens with a big telescope look at our solar system from, say, 30 light years away, distance of a nearby star. Probably they could not image the Earth at all, but if they had a big enough telescope to do this, then the Earth would look, in Carl Sagan's nice phrase, a pale blue dot, lying very close in the sky to its star, our Sun, and 1 billion times fainter. So the aliens would be looking for firefly next to a searchlight, as it were. But if they could detect the pale blue dot and observe it, they could learn quite a bit about it, because the shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could infer the length of the day, that there were continents and oceans, maybe something of seasons and climates, maybe by analyzing the light, something about the atmosphere, whether it had oxygen in it. Well, we can't do that yet, but with a big telescope being built by European astronomers here, it'll be possible. This is a sketch of a telescope being built by European astronomers, which will be ready in 10 years' time. They're not very original in their nomenclature. It's called the Extremely Large Telescope, the ELT. And it's got a mirror which is 39 meters across, and that's about twice the length of this room. Not one sheet of glass, but a mosaic of 800 sheets of glass. And this instrument would be capable of making observations like I've just described about Earth-like planets around nearby stars. That would be very exciting indeed. But of course, the question everyone asks is, will there be life on any of these Earth-like planets? Because being habitable is not the same as being inhabited. And it could be, of course, that life is something which only happens very rarely. And this is a question to which we don't yet know the answer. We understand Darwinian evolution, but we don't yet understand what made the transition from biochemistry to the first replicating, metabolizing systems that we call alive. People are working on this, but we don't know, so we can't say whether it's likely or unlikely, nor whether the only possible chemistry is the DNA, RNA that we have. And the other question, of course, is that even if it's a simple life, we don't know what the chances are of it evolving into something which would be complex or interesting, even something that might be intelligent, sending out signals to us. Of course, there are some people who know this answer already. I mean, one of the downsides of being astronomer royal is I get letters from people, some of whom say they're being abducted or they met the aliens and all that. I say two things to these people. I say, do they really think that if the aliens had made the huge effort to traverse interstellar space to get here, would they just have met one or two well-known cranks, maybe made a corn circle and gone away again? Seems unlikely to me. And the second thing I say is they should write to each other and not to me. But these issues will be clarified. We know about simple life, and there is a big project being funded by a Russian billionaire to have a more intensive search for any kind of artificial signals coming from elsewhere, and I've agreed to chair the advisory committee. I'm not holding my breath for success, but I think we should thank him for spending his money on this rather than on a football team or a bigger yacht. $100 million he's put in this project. Going back to the planets, we've had a sort of second Copernican revolution in the sense that we now know that our solar system is not special and that there are literally billions of solar systems. This is the Milky Way, which contains 100 billion stars, and a large fraction of them will have planets, and there will be a billion planets like the Earth in our galaxy. But just finally, I want to mention two other Copernican revolutions. The first is that, of course, we now know that our Milky Way is just one galaxy among many others. This is Andromeda, the nearest big galaxy to us, this is another galaxy, and we have this map of all the galaxies within 500 million light years. And we can see very far away. This is a picture taken with a big telescope, which shows a tiny patch of sky. It would take 100 patches like this to cover the full moon. This is about 3.5 minutes across. But in this tiny patch of sky with a big telescope, you see these hundreds of smudges. Each is a galaxy, many fully the equal of our galaxy, or the Milky Way, but looking so faint because of the huge distance there. These galaxies sent out their light when they were young, about 11 or 12 billion years ago. And so we can actually do better than geologists. We can actually observe the past and understand how galaxies evolve. And this has led us, along with other evidence, to the Big Bang theory of the universe, which I don't have time to go into, but we have a picture where we can trace things back to a hot, dense beginning. We can trace things back with some confidence to when the entire observable universe was squeezed down to the size of a solar system. That's when every particle had about the energy we can produce in the LHC. But some of the key features of the universe, why it's expanding the way it is, why it contains the mixture of atoms and radiation that we observe, the answers to those lie far earlier still, right back when the entire universe was squeezed, not to the size of a solar system, but literally to that size. And this, of course, is speculative science, but that's what people like Harvey Ryle are working on. And this will involve understanding the links between Einstein's theory of the very large and the microworld. And this, I like this Ouroboros picture. This shows the very small on the left and the very large on the right, where the quantum world is the left-hand side, the world of gravity is on the right, and we got on quite well by not having a unified theory, because a chemist doesn't need to worry about the gravitational pull between the different atoms in a molecule. It's 40 powers of 10 weak electric forces. Conversely, an astronomer doesn't need to worry about the quantum fuzziness in the orbits of planets. They're so big. But if you want to understand the very beginning of the universe, then we have to go back to when the universe was so small that, as it were, quantum fluctuations could shake the universe. And to understand that, we need this synthesis symbolized gastronomically at the top between the quantum world and the cosmos. And that's what people are working on now. It's one of the important bits of unfinished business for 21st century physics. Before leaving this, I'd just like to have a bit of sort of modesty, because particle physicists work on the left, and astronomers work on the right-hand side, but only 1% of astronomers, only 1% of scientists are either astronomers or particle physicists. 99% of scientists work on the frontier, not of the very small nor the very large, but of the very complex, and that's at the bottom. And the most complicated things we know about are human beings. And even an insect is harder to understand than a star or a galaxy. This is the famous flea, drawn by Isaac Newton's least favorite colleague, Robert Hooke, in his classic book Micrographia. And even the flea has a layer upon layer of intricate structure, far more complicated than anything inorganic. So it is a challenge of complexity, which is the focus of most scientists' work. And just finally, I mentioned that the third Copernican revolution was many galaxies, but some people think we can go one step further, and that our Big Bang is not the only one, and that our universe is symbolized there, going out as far as we can see, but maybe it's part of some great archipelago, some infinite ensemble of Big Bangs. This is so-called multiverse idea, which I certainly can't explain in the -1 minute I have left. So let me just finish by focusing back in from the universe, a multiple to the universe, to the Earth. I'm sometimes asked, do scientists have, in particular do astronomers, have any special perspective? Well, I've lived much of my life among them, and I can assure you that the fact that they contemplate vast expanses of space and time doesn't make them any more relaxed or serene. They fret just as much about minor matters as anyone else. But there is one difference, and I want to finish by mentioning it. It's that they are aware of the huge future lying ahead. This is a time chart of Darwinian evolution, 4 billion years since the first life, and I think this is familiar to all of us, unless you live in Kentucky or parts of the Muslim world. But even those who are happy with this tend to feel that we are somehow the culmination. And no astronomer could believe that. Because as this time-lapse picture illustrates, our sun formed 4.5 billion years ago, and it's got about 5 billion years ahead of it before it flares up, engulfs the inner planets, and runs out of fuel. So the future for our sun is longer than its past, and the entire universe may go on forever. And to quote Woody Allen, eternity is very long, especially towards the end. So any creature sending back this postcard when the sun dies won't be human. It'll be as different from us as we are from a bug. Even Darwin, a much nicer scientist than Newton, although he might have done less well in an IQ test, he realized that no present species will survive into the distant future. And we would strengthen that, because I think future evolution, here on Earth and far beyond, is going to be not on the Darwinian natural selection timescale of millions of years, but on a much shorter technological timescale of humans adjusting their own genome and perhaps machines taking over and developing further. So future evolution is going to be far more exciting and far more varied than what's happened up to now. So we are just the beginning. But having said all that, I want to say that in this concertina time span, going billions of years into the past and into the future, this century is a special one, because it's the first in the Earth's 45 million centuries, when one species, namely ours, has the planet's future in its hands. And so this is a reason why we should feel a special responsibility, because it'll be what humans do now which determines whether this huge future happens or is foreclosed. And so with that thought, which I think is important for non-astronomers as well as astronomers, let me close. Thank you very much indeed.